So hello everybody, this is the next video about coprime numbers or so-called relatively prime numbers and Bezouts identity. So if you remember, if you take two numbers a and b as integer numbers, then you can compute the GCD, the greatest common divisor of a and b, which will be equal to some number d. Well, sometimes it happens that if the GCD of a and b is equal to 1, then the numbers a and b are called coprime numbers or relatively prime numbers. That is, they share no other divisor than 1, then they have no other prime number or no other number as a common divisor. So this will be important because coprime numbers will be very useful, especially regarding RSA, the crypto system RSA we will see later. So don't be confused between the difference between a prime number, so a number alone can be prime or not, and two numbers can be coprime or not. And actually, this has nearly no relation between a number being prime and two numbers being coprime. For example, let's take two numbers, a is equal to 21. Actually, it's equal to 3 times 7, so a is not a prime number because it has divisors here, 1, 3, 7, and 21. b, let b be equal to 55. 55 is 5 times 11, so b is not a prime number. Actually, if we try to compute the GCD of A and B, which is the GCD of 21 and 55, according to the list of divisors, we can very simply express from the fact that 21 is 3 times 7 and 55 is 5 times 11. Actually, their GCD is equal to 1. So A and B, thus 21 and 55 are coprime. But neither 21 nor 55 is a prime number. So pay attention not to confuse the notion of prime number. This is about a number itself and alone, and coprime numbers, which depends on the value of their GCD. Okay, next, let's talk about a very important feature, which is Bezouts identity. Actually, there are a lot of theory about Bezouts identity. We don't need much of that theory. Let's just express it and see what we can withdraw from this identity. This identity states the following thing. So for all couple A, B as integer numbers, there exists a couple of so-called coefficients u and v such that a times u plus b times v is equal to the GCD of A and B. Okay, from this definition, what we will withdraw is that sometimes, namely in a few videos to come about computing an inverse modulo some value of n, sometimes we need to know the couple u v to compute inverses, and this has a relation with respect to cryptographic keys. We'll see that later. Actually, Bezout's identity will be used later in order to compute some keys for a crypto system. And actually, we won't need the value of the GCD, but from a practical point of view, let's be pragmatical here, we also have a method to compute U, V, and also the GCD of A and B from the values of A and B. So what we've seen before is that actually we know how to compute the GCD of A and B from A and B, and the GCD of A and B can be obtained from the Euclid algorithm. So it's been explained, and you have some examples as a video of how to proceed and process for the Euclid algorithm. Now, if you want U, V, and perhaps the GCD of A and B, actually, there is quite an extension or some enhancements to proceed to the extended Euclid algorithm. So this will be part of the next video, how to compute a couple of coefficients U and V and the GCD, because it's also part of the algorithm from the value of A and B.